Hello, and welcome to another lecture in this course. So today we're going to look at Cauchy's theorem for star-like sets. So this is subsection 3.2.3 in the book. So what is star-like? So star-like, talking about domains U, right? So open sets U, and we suppose that there's a point Z0 in U, and it's star-like with respect to this point Z0, or it's star-like if you don't specify the point, but there is some point, one point, such that every segment from Z0 to Z is in U for any Z in U, right? So the idea is the following, and that's sort of where the name comes from. It, sort of, you think of it as a star, with Z0 being kind of the center of the star, right? And so any point in the set, the line from Z0 to that set, to that point is in the set. So it's not quite convex. So convex sets are star-like. They're star-like with respect to every point. But I mean, this set over here is not convex, right? I mean, the line between these 2 points is not going to be inside this set. But there's at least one point in this set that, with respect to which it is star-like. Actually, for this set, it's a bunch of points, but it's also, it's like a star-like. It's a museum that can be watched by a single guard. Right, a single guard sees every point in the museum, right? All right. So, what are we going to prove? Well, what are we going to prove first? So, if we have this star-like U, right, and a continuous F, such that for every triangle, and here again we were talking about the solid triangle T inside U. So for every solid triangle T in U, we have that the integral around the boundary is 0. So if that's satisfied, we have that F has a primitive, meaning that there is a holomorphic capital F whose derivative is F, right? We can anti-differentiate this little f, right? All right, so let's suppose that we have a star-like U, right? So it's star-like with respect to some Z0. Right? And so let's just define what capital F is. Little f is continuous. So these things make perfect sense, right? These kind of integrals. Right, and this is a well-defined integral, right? I go from Z0 to Z along a straight line. There's no choices to be made here, right? This is a well-defined number for every Z. I have a number, right? So let's define capital F this way, and let's prove that that actually happens to be the antiderivative of little f. Right, that's the capital F that we're looking for. All right, so let's look at some Z. Let's look at some disk of radius little r around Z, right? And let's suppose that this is inside U. So we're gonna, look in some neighborhood of some point. And let's suppose that H is a number, is a complex number, which is in modulus less than r. So basically, Z plus H is in this disk, right? Maybe it's better to see a picture. I have some Z, right? This is the disk, right? And H is so that Z plus H is still inside this disk. Now, Z0 is some point, some given point, right? With respect to which U is star-like. Right? Now, since U is star-like with respect to Z0, and the entire segment from Z to z plus h is inside this disk, therefore it's in U, right? We get that everything, right? Basically, every straight line over here is inside U, meaning the entire triangle, right? This entire, even the solid, inside, the entire solid triangle is in U, right? So the entire triangle is these vertices, z0, z, and z plus h, right? Now, by hypothesis, we were saying, what was the hypothesis, right? The hypothesis was this thing. For every triangle T, I have that the integral is 0, right? So, yeah, that's what we have. That's how I write the outside triangle, right? The boundary, the non-solid triangle, right? The boundary of this triangle is this cycle over here, right? So I start at z0, go to z, then go to z plus h, and then go back to z0, right? So let's look at, we're trying to show that the derivative of capital F is little f, right? So let's look at the difference quotient, right? Well, and let's write it down. Now, if I have, what is the definition of this integral, right? Is the integral over this guy plus the integral over this guy minus the integral over this guy. I wrote it as minus because it's really the guy. I'm supposed to be going from z plus h to z0, so that's the same thing as minus z0 to z plus h, right? So if I look at right, so what is this thing, right? That's basically this guy. And what is this thing? That's basically this guy, right? And the minus sign, well, that's the minus sign in between, right? That's how chain integrals work, right? And I'm dividing by h, I'm dividing by h. So really, I'm just writing the difference quotient in a slightly funny way. Now, this thing says that if I take, this thing minus this thing, right? That integral is the integral over this middle guy, right? That's coming from this this equation up here, right? So far so good. So that's the integral over this little piece inside this disk, right? This little piece. Let's maybe go back. It's the integral over this little piece in the picture, right? And that little piece is would be, could be tiny. And actually, we're trying to make that tiny because we're trying to make h go to 0, right? Okay. So what is this guy by definition? Well, let's just, write down the usual definition of, parametrizing a segment, right? Just affine linearly, right? So the derivative then becomes this h, right? Well, that's convenient. That cancels out here, right? So we have that the difference quotient is given by this formula, right? All right. So let's see what it goes to, right? So it's supposed to go to little f, right? So let's subtract the difference quotient and little f, right? So, okay, so the difference quotient, that's this guy. Let's write little f at z in a funky way. Let's write it like this, right? F of z is really a constant here, right? We're integrating with respect to t, right? Integrating from 0 to 1, so that's, that's 1, right? So times f of z, that's f of z, right? So it's just a funky way of writing the f of z. Now, the reason for doing that is so that I can I can write this as a single integral, and I'm gonna just, use the triangle inequality for integrals, right? and bring the absolute value inside, right? So I get this integral over here. Now, the thing is that this h is, I'm trying to let h go to 0, really, right? So this is going to be a really small thing, right? By continuity of f, right? If I'm picking h very small, right, then this is going to be very small, right? For any t between 0 and 1, right? I'm just looking at the values of f on this little interval, right? But just the delta epsilon of continuity, right, will make this work, right? So by the continuity of f, little f at z, I get that the derivative of capital F is little f at z, right? And so we're done. Now, if we now look at Cauchy-Grosset, which was that the integral around triangles for holomorphic function is 0, right? So we take a holomorphic function and we integrate it around a triangle. As long as that entire solid triangle is inside U, then then we get a holomorphic. Then we get 0. Sorry. So if we put those, the proposition that we proved and Cauchy-Grosset together, we get that if U is open, now you have to put the star-like in there, and F is holomorphic. F being holomorphic implies that the integral around triangles is 0, so we can apply the proposition that says that F has a primitive, right? This capital F exists, right? So for any star-like domain, right? And I keep saying domain, even though I say open here, but once it's star-like, it's going to be connected. So domain. For any star-like domain, any holomorphic function has a primitive. And you notice that this thing didn't have anything to do with integrals, right? So you proved something that suddenly doesn't have any path integrals in there, right? Okay, so with that, we get Cauchy's theorem for star-like domains, right? Meaning if U is a star-like domain, F is holomorphic, and gamma is any cycle in U, absolutely any cycle in U, then the integral around this cycle is 0, right? So before we had the Cauchy for triangles, and those very, very, very special cycle, right? This is absolutely any cycle, right? And we get that the integral is 0. How does this work? Basically, we're done, right? It's if you think about it, the corollary says that there is a primitive, and we have Cauchy's theorem for derivatives, right? So because little f is a derivative, because it has a primitive, right? We had Cauchy's theorem in that setting, right? So we have Cauchy's theorem in this setting, right? By proving that every holomorphic function in a star-like domain has a primitive, we get Cauchy's theorem. Now again, Cauchy's theorem doesn't work for any open set, any domain, and any holomorphic function. There has to be something, right? So for example, being star-like, right? There's going to be better conditions later on. This is the one that we have right now, right? So if U is star-like, then you get Cauchy's theorem, right? All right. Now, just as a remark, if you if the proof seems familiar, you might have seen this in a vector calculus class, because it's basically a version of this theorem about vector fields, is that if you have a star-like domain, and sometimes it's given not for a Starlight domain, but sometimes it's proved for like a special domain or convex domain or something like that, for a ball or something, disk in this sense. And you have a continuously differentiable vector field that is irrotational, which means for a vector field UV, in terms of the variables x and y, it means the y derivative of u is equal to the x derivative of v, which is basically, that's the necessary condition for the vector field to be a gradient of something. So, well, there's a theorem, and the proof is basically what we just did, showing that well, there is actually a real valued function whose gradient is this vector field, meaning it's a conservative or a gradient vector field, right? It's exactly that, right? You're doing this thing around triangles. So if you've seen that, if it feels familiar, it might be because you've seen it before, right? All right. So next time, what we're going to look at is we're going to look at the Cauchy's formula, Cauchy's integral formula for disks, meaning that we can write down the value of a holomorphic function in terms of its values on the boundary of a disk. And, later on, we'll prove it for more complicated sets, but next time we're going to do it in a disk. And actually, many times you just use it in a disk anyway. So that's coming next time. All right. So see you then.